So we load the Saturn model, we load its rings, we load a whole bunch of its moons, and somewhere tucked away is the Cassini spacecraft. There it is right there. Let's go and fly it on board. We actually got a guy called Brian from the games industry to make these models because we knew that we were falling short in that regard, and we're actually really throwing some full-on game industry texturing on these things. The gold foil seems ubiquitous with spacecraft, and it was a bit of a challenge, but we think it was looking pretty beautiful. I'm going to turn off these extra planets in the background. It's getting a bit noisy. Let's hide those. That's better. And so here is the Cassini spacecraft right now. If you could ride on board, this is the view you'd have right now. But Cassini's been there since 2004, so we can relive 6, 7, 8 years of exploration right in your browser. So let's go and recreate one of the flybys that it's had. Let's go and look to October 2008. Cassini flew past one of the moons called Enceladus, that if you didn't know better, you'd think it was spelled like Enceladus. This is a distance of about 25 miles. That's something like 50,000 miles per hour. This is that flyby in real time. If you'd have been on board, this is what you've actually seen, not accelerated, in real time. It got the same response from the actual mission scientists. We can get back out to look at Enceladus and see Cassini right next to it. There it is. We can pause time. We can measure the distance between them. So now we have a virtual tape measure across space that stays there, and we can run the flyby backwards, we can run the flyby forwards, and you'll see the measure move in real time. Now so let's go look at a mission from the future. Let's go look at something called JEO, the Jupiter Europa Orbiter. Now this is still a proposal, it's not an actual firm mission, but Europa being one of the most fascinating places in the solar system, it's kind of high on our list of priorities as somewhere to go and look at. So we hit JEO. It takes us into the future, because JEO hasn't launched yet, doesn't even exist yet. We're now in 2020, and JEO has just launched. There it is. And we've actually tucked away a series of little bookmarks to show us its predicted trajectory, the kind of the straw man, what's this mission going to do trajectory. And we can do its flight all the way out to Jupiter. I'm now hands off. We've got a script running that does the whole trajectory for us. We leave the Earth. We take a swing around the solar system, slingshot past Venus, back out towards Mars. The slingshot past the Earth, letting Isaac Newton do all of the driving. Back out, this is about 2 AU from the Sun at this point, back in towards the inner solar system, another slingshot of the Earth, and then we're out all the way to Jupiter, because a big spacecraft takes a lot of energy, and you can't pack it all into one rocket. Once we get to Jupiter, the approach is going to involve some of the moons. We're going to use the moons as slingshots to adjust the orbit of this thing around Jupiter to eventually synchronize up with the orbit of Europa. So somewhere around here, hopefully I can find Io. Where is it? Well, you know, I've lost the moon. There it is.
Just to the left of Europa.
Io encounter. Let's try again. There we go. And so now we're riding on board JEO, looking at Io. 5 minutes, fantastic. Notice the high gain antenna is actually tracking to the point of the Earth, so it's downloading data all the way. So that's missions from the past, present day, and the future. And what we've also done is bolt in features to help people follow along with missions in real time. We've done this twice so far. We were involved in the Deep Impact flyby of Comet Hartley 2 back in November, and the Stardust Next flyby of Comet Temple 1 actually on the evening of Valentine's Day. And we bolt these into tours and features. And I'm going to take you live on board the Stardust flyby, as if you'd have been there on the night of February 14th. In fact, we were asked to use this not just for the public to use in their browsers, but also so that people could follow along in real time on NASA television as well, because we've got right within this the abilities to do all of that. We have to load the Comet, we have to load the spacecraft, and I can't see the keyboard because it's too dark. Thanks, Kevin.
Tip the screen down a little bit.
Yeah, let's go there.
Also, they can't see the right side either, so you have to use the TV mode.
Thank you. Let's do that. Here we go. So this is what we are using on NASA TV live during the night of the flyby, and we baked into it shortcuts to show the 5 closest approach images. Our 3D guy made a model of the Comet Nucleus. This is a part of the Comet we'd seen some years before, and this is the part we haven't seen before. Here's the spacecraft with its camera, and its antennae pointing back towards the Earth, a wide, medium gain, and a high gain antenna And if we run the flyby accelerated, this is the camera field of view, here's the spacecraft, this is the camera right here. And you'll see that camera actually turn to track the comet nucleus as we went past. If I let it run in real time, you'll see every green flash was a commanded image, every 6 seconds or so. The extraordinary thing was that on the night of the flyby, the images were actually downloaded in the wrong order. We were expecting to get the closest ones first for the benefits of the media, but actually they started downloading the first one. So we started with an image from many thousands of miles away, and the nucleus was just a tiny little fuzzy grey chicken nugget in the middle of the screen. And the scientists, desperate to know whether or not they were going to see the side of the comet they wanted to, were behind my colleague John and I at our workstation with emission control, comparing this view with that first image, and we're very actually pleased that we were able to confirm that we were seeing the right side of the comet. We actually embedded it so that we could flip the comet backwards and forwards like this to try and match what the images showed, so that were the images coming back the wrong way, we just make sure we were showing people what they were actually expecting to see. Now, that's my demo for Eyes on the Solar System done, because what I want to do is show you just a little bit of a treat. This is something that isn't released yet. It's not going to be released for probably a couple of weeks, maybe a month or two. But this Thanksgiving, we'll be launching our next Mars rover called MSL. And August next year, we'll be landing at one of 4 potential landing sites on the surface of Mars. And we're working, of course, on a beautiful rendered animation to explain to people how that mission is going to work. There is one existing already. There's a mission animation out there. This is the updated version. This is going to be official project animation as of a few months' time. But to give you an idea that it really is still in progress, this is a highly compressed, without soundtrack video. Let's go full screen. And I'm going to cheat and just take you to the entry, descent, and landing part of this animation. It's absolutely spectacular. This is how you land a spacecraft that's the size of a Mini Cooper and weighs 2,000 pounds onto the surface of Mars. It's not easy. So, this is the cruise stage. It's the thing that takes you all the way to Mars. It gives you the power, the propulsion, the communications you need to get there, but not once you arrive. What we're left with is a heat shield that's larger than the heat shield used to bring people back from the moon. This is a larger capsule than the Apollo capsule. It's only no bigger, because it wouldn't fit in the rocket if it was any bigger. You arrive in the atmosphere about Mach 25, and there's a very, very thin Martian atmosphere, but it's enough to take away about 95% of your speed, 99% of your kinetic energy. And for the first time, we're going to use a guided entry. We're going to manage our energy using an offset center of gravity and center of pressure, so we can target a specific landing site. Instead of a 100 by 20 kilometer ellipse, it's going to be a 20 kilometer circle, so there are more places we can potentially land. That's what those thrusters are doing there. They're managing the energy, turning the spacecraft left and right. We can use ballast to offset at the beginning, we use ballast to then rebalance the spacecraft. Throw out a supersonic parachute. This thing's about 100 feet across. It's fired by a mortar. It's genuinely an explosion that fires this thing out of the back of the spacecraft. We get rid of the heat shield. It's done its job. At this point, about a ton of spacecraft is hanging off a parachute. It's falling at about 250 miles per hour. At that point, we drop the spacecraft out of the back shell, about a kilometer above the deck. And notice the rockets are on top of the rover, because if you put them underneath, when you land, your rover's going to be about 2.5 meters above the ground. How do you get it down again? And this thing uses throttled engines. It's going to fly itself, avoiding the back shell, come to a point above the ground, taking images as it descends. But even not, this thing has a camera that will take 1600 by 1200 pixel color images at about 5 frames per second all the way to the deck. It's going to be a hell of a movie. Here is that camera on the underside of the rover. You can see the thrusters still doing their work. We're still tucked up, nestled underneath this rocket jetpack called the descent stage. Here's our emulation using real elevation data. That's a real patch of Mars, in fact, using stereo data. And then, this is the bit that gets people nervous. Now, it's going to be under this rope for just a few seconds. Yeah, it sounds crazy, but it is, in fact, just about the most sensible way of getting the rover onto the deck, because if you put it on top of the rockets, how do you get it onto the ground? You need to have landing legs, you need to have ramps, you need to try and get it off somewhere. You have to spend a huge amount of mass and energy doing that. By just asking the descent stage not to come to a stop on the ground, but come to a stop 10 meters up, the lander doesn't care where that is. We can then lower the rover onto the ground, deploy the suspension. At that point, we're ready to go. So this animation goes on for another 12 minutes. I'm not going to bore you to death with it, but look for this. This is the next Mars rover, and that's all from me, because I think we're out of time.